I find this a fascinating object. It's a fiber optic cable for a stereo. If I shine this laser pointer down the cable, it guides the light out the other end. These cables are used to connect our world today and are capable of transmitting information across countries and oceans. But first, let me show you how it works. I have a bucket that I've modified with a window in front. And on the other side, I put a stopper in this hole right here. I have a bottle of propylene glycol with just a little bit of creamer in it. A ring stand. And of course, a laser pointer. Now, keep your eye on this plug when I turn out the lights. That's wonderful. The light follows the liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection. As the light enters the stream, it is reflected as soon as it hits the interface between air and liquid. You can see here the first reflection, and then the second, and the third. This occurs because there's a difference between the index of refraction of the guide material, here propylene glycol, and the outside, air in this case. Recall that any time light strikes a surface, it can either be absorbed by the material, reflected from it, or pass into and through it. The latter we call refraction. It's easier to see from a top view. Reflection and refraction can happen at the same time, but if a light ray hits the surface at an angle greater than the critical angle, it will be completely reflected and not refracted. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection. To create this same effect in an optical fiber, engineers create a core of glass, usually pure silicon dioxide, and an outside layer called cladding, which they also typically make from silicon dioxide, but with bits of boron or germanium to decrease its index of refraction. A 1% difference is enough to make a fiber work. To make such a long, thin piece of glass, engineers heat a large glass preform. Its center is the pure core glass and the outside the cladding. They then draw or pull a fiber by winding the melt onto a wheel at speeds up to 1,600 meters per second. Typically, these drawing towers are several stories tall. The height allows the fiber to cool before being wound onto a drum. One of the greatest engineering achievements was the first ocean-spanning fiber optic cable. Called TAT-8, it extended from Tuckerton, New Jersey, following the ocean floor over 3,500 miles until branching out to Whitmouth, England, and Ponmarsh, France. Engineers designed the cable carefully to survive on the ocean floor. At its center lies the core. Less than 1/10 of an inch in diameter, it contains 6 optical fibers wrapped around a central steel wire. They embedded this in an elastomer to cushion the fibers, surrounded it with steel strands, and then sealed it inside a copper cylinder to protect it from water. The final cable was less than 1 inch in diameter, yet it could handle some 40,000 simultaneous phone calls. The essence of how they send information through a fiber optic cable is very simple. I could have a prearranged signal with someone at the other end. Perhaps we'll use Morse code, and I just block the laser so that the person at that end sees flashes that communicate a message. To transmit an analog signal like voice from a phone call along the cable, engineers use pulse code modulation. We take an analog signal and cut it up into sections and then approximate the wave's loudness or amplitude as best we can. We want to make this a digital signal, which means discrete values of loudness and not just any value. For example, I'll use 4 bits, which means I have 16 possible values for the loudness. So the first 4 sections of the signal could be approximated by about 10, 12, 14, and 15. We then take each section and convert its amplitude to a series of ones and zeros. The first bar of value 10, when encoded, becomes 1, 0, 1, 0. We can do this for each section of the curve. Now, instead of looking at the green waveform or even the blue bars, we can think of the signal as a series of ones and zeros organized by time. And it is that sequence that we send through a fiber optic cable, a flash for a 1 and nothing for a 0. Of course, the exact method of encoding is known at the receiving end, so it is a trivial matter to decipher the message. Now, you may be wondering how a laser pulse can travel nearly 4,000 miles across the ocean. It doesn't without some help because the light will escape from the sides of the fibers. Look back at our propylene stream. Here's how the light attenuates as it travels. You can see here a narrow beam in the bucket that broadens a bit when it enters the stream, and then after the first bounce, the beam leaves even broader than it entered. That's because the interface with the air is uneven and the rays that make up the beam strike at slightly different angles. When that beam makes its second reflection, those individual rays diverge even more, until by the time it reaches the third bounce, many of the rays are no longer at the critical angle and can exit from the sides of the stream. Here it happens in a few inches, but in a cable like TAT8, the signal travels a stunning 50 kilometers before it needs to be amplified. Absolutely amazing. I'm Bill Hammack, the Engineer Guy.